Hi everyone. In today's video, we will be covering information from both chapters 9 and 10, which covers bivariate tables and chi-square. Over the last several videos, we have discussed several ways in which we can use sample data to estimate population parameters. We started off in chapter 7 by discussing confidence intervals, which tells us that the population parameter, whether that is a mean or a proportion, lies within a certain range of values. We then moved forward to chapter 8, which was our introduction to hypothesis testing, both with regard to one sample and two sample tests, and if we're doing that for sample means or proportions. What we'll be doing today is also a version of hypothesis testing, but with a new concept in mind called chi-squared. A chi-squared test is a statistical test of independence used to determine whether there is a significant association between two categorical variables. And because we have to use categorical variables in this specific type of hypothesis testing, they will need to be nominal in their level of measurement. We can also use ordinal level variables if they mirror a categorical framework, but mostly we'll be using nominal level variables throughout the duration of this video and whenever you need to identify a chi-square test. Essentially what we're doing is asking whether variables have a relationship to one another, or in other words, are variables independent or dependent on each other? Do they have some sort of relationship, or are they completely separate from one another? An example of this is, are zodiac signs independent from personality type? So essentially what we're doing there is measuring whether or not these two variables have some sort of relationship or association with them. With a zodiac sign, that's based on your date of birth, and with a Myers-Briggs test, you're able to measure various components of your personality. And so we'd be able to see statistically whether these two things have any actual statistical association to one another. You'll notice that in both this example and the next one, which is gender related to marijuana use, we are using nominal level variables. Zodiac signs is nominal, right? It's just corresponding to what your birth date is. Personality type is the same way. It's not measured on any sort of ranked order or has any sort of interval or numerical value attached to it. Same with gender and marijuana use. Gender is a male-female binary, where marijuana use is a yes-no. Are you using it or aren't you using it? And again, we can use chi-squared to measure whether these variables have any relationship to one another. Before we dive into actually conducting chi-square tests of independence, we need to revisit this idea all the way back from chapter 2 of bivariate tables or crosstabs. Bivariate tables allow us to display frequencies for two nominal or ordinal level variables, and we typically include the independent variable in columns and the dependent variable in rows. So let's take a look at our example below. Within our column category, we have our independent variable of gender, and gender is measured at the nominal level. We know this because there are two distinct categories, male and female, and there is no inherent ranked order or numerical attachment. What you see here, though, in terms of our dependent variable is actually an example of how we can use an ordinal level variable with respect to chi-square. So with weekly marijuana use, we have a scale ranging from never to often. And so we know that this is measured at the ordinal level because someone that has never used marijuana uses less marijuana on a weekly basis than someone who uses it often or occasionally. We know it's not an interval ratio level variable though, because we can't quantify the differences between these categories. And so, again, all that we're doing here is displaying these two different variables, and each respective frequency displays how often a single observation falls into each respective category. And so from this sample of a total of 31 individuals, we know that 5 males reported that they often use marijuana on a weekly basis, and so on and so forth. And this is going to be the basis that serves for our chi-square test of independence and how we'll calculate this later on. In order to conduct a chi-square test of independence, we essentially have to compare two things to one another. The first being observed frequencies, which are designated by F with a subscript of O for observed. These are our actual frequencies in our data or that are displayed within our bivariate table. So there's no statistical analysis that we actually have to conduct in this case. For example, within our sample of 31 individuals, we had 3 females respond that they often use marijuana on a weekly basis. So that's just what occurred. There were 3 individuals that were female that indicated that. We also have to compare this, though, to our expected frequencies, which is designated by F with a subscript of E for expected. These are the frequencies we would expect to see if the 2 variables of gender and marijuana use were independent, given random chance. With that being said, in order to conduct a chi-square test of independence, we only need the 2 elements we discussed on the previous slide in order to calculate it. That is our observed frequencies and our expected frequencies. So our test statistic, or our overall chi-square obtained, is going to be measured given the summation of all of our observed frequencies subtracted by our expected frequency squared divided by our expected frequencies. But how do we get expected frequencies? This is the only calculation we need to do in order to figure out our chi-square, so let's discuss that below. Our expected frequency is our row marginal multiplied by our column marginal divided by n, or the total of our sample. So what do I mean by marginal here? Essentially, think of the term marginal as total, so your row total multiplied by your column total. So let's take this first cell here in our top left corner as an example. These are males who reported that they often use marijuana on a weekly basis. And so our row marginal comes from the total of individuals that reported that they often use marijuana on a weekly basis. So we have 8 individuals that reported that. We then need to look at our column total, or how many males are in this sample, which is 16. So that's where I'm getting these 2 numbers here in our numerator. We then need to divide that by our n, or our sample total, which was 31 individuals who were included in this sample. And so our expected frequency, or what we would expect to see if these 2 variables were completely independent of each other, is 4.129. And in order to conduct that chi-square, as I mentioned right off the bat, we have to sum all of these together. And so once we determine our expected frequency, we can then plug that into our original equation up here and add those all up together. I think that'll make a little bit more sense as we move forward with an example in a few slides, so hang on tight to that for just now. To conduct a chi-square test of independence, we have to adopt the same 5-step model of hypothesis testing that we've used in previous chapters, whether that was for 1 sample or 2 sample, or for means or proportions. But in this case, we'll be using it for chi-square. So as always, our first step is to make assumptions. This will look a little bit different now that we are using chi-square rather than our previous types of hypothesis testing, but we'll get into the specificities of that in just the next slide. Our second step is to state our null and research hypotheses, as well as to select our alpha level. But again, this will always be given to you within the context of the problem. Our third step is to select our sampling distribution. And even though we have the Z distribution at our disposal, whether that's for 1 sample or 2 sample tests, and whether we're conducting that for means or proportions, we will now be introducing the chi-squared distribution and specify that corresponding test statistic. Our fourth step is to compute that actual test statistic. And again, we will only be using the chi-squared test for the purposes of this presentation and model. Lastly, we make our decision and interpret the results within the context of the problem. In other words, are we going to reject the null hypothesis or fail to reject the null hypothesis? Our first step to conducting a chi-square test of independence is to make our assumptions, and we have 2 central ones here. The first is that we are working with independent random samples. Now, we've seen this assumption with regards to other forms of hypothesis testing, but it is especially relevant in this context because what a chi-square test is doing is evaluating whether there's a relationship or an association between 2 variables. In the context of this course, you can always assume, whether it's a problem set or a quiz, that the two variables I will be giving you are independent and random. However, if you were to conduct a chi-square test in a real-world setting or data set, you would want to ensure that the two variables you are using are both independent and randomly selected. Our second assumption is that our level of measurement is nominal or sometimes ordinal, and we saw the use of both of these in our last example when we evaluated whether gender and weekly marijuana use had any relationship to one another. We had the nominal level variable of gender, but we also saw that weekly marijuana use was measured at the ordinal level because we had a Likert scale ranging from never to often. There were categories that could be ranked, but they didn't have a numerical attachment to them. In other words, we couldn't quantify the differences between each of those uses. Importantly, even though we've had a different type of assumption when it comes to one sample and two sample hypothesis testing of a normal distribution, we do not have that requirement with regards to chi-square. The reason being is that our chi-square distribution is not set on a normal curve. We'll get to that in just a moment, but just keep that in mind. We do not have that third assumption of the requirement of a normal distribution in a chi-square format. Our second step is to state our null and alternative hypotheses. And so this language of our statistical notation should look familiar to us. We are still keeping the same format of H with a subscript of 0 to designate our null hypothesis. And within a chi-square test, our null hypothesis is simply that the variables, and going back to our example about gender and marijuana use, are independent from each other. Again, our null hypothesis is our statement of no difference. And in this case, our null hypothesis is always going to be that there is no relationship or that two variables are independent unless shown otherwise. And so our research or alternative hypothesis, which is still designated by H with a subscript of 1, is the exact opposite of that. The variables of gender and marijuana use are dependent on each other. So if this is the case, the differences between the observed and expected frequencies will be large. So keep that in mind as we are working through the actual calculations of our computation of our test statistic in step 4. I had previously mentioned on the last slide that a chi-squared test does not have the same assumption about a normal distribution. Reason being is that the chi-square distribution is always going to be a one-tailed test, and it's shaped like this. You don't need to know the background of why a chi-square distribution is shaped like this. Just know that it is, and that it will always just be the positive end of our distribution here, and that's all you'll need to be concerned about. We won't have a two-tailed test where we're concerned about whether it is on the positive or negative end. It will always be a one-tailed test. And because of that, there's going to be this extra step of degrees of freedom that we'll have to determine, but we'll do that next in step 3. Our third step is to select our sampling distribution and establish our critical region. Whenever we conduct a chi-squared test for independence, we will always be using a chi-squared distribution rather than a normal distribution. Remember from step 1, we do not have the same assumption of needing a normal distribution because the chi-squared distribution looks different. It's always going to be a one-tailed test, and we are only interested in the positive end of the distribution. With that being said, we have a different table that we'll need to use in order to establish our critical region or our barrier cutoff for our rejection zone. And that is Appendix D. This is available both in your book and posted to Canvas, and we'll go over how to use this in just a moment. There are two elements that we'll need to determine in order to use Appendix D or our chi-square table. The first is called our degrees of freedom. And this is a term that refers to the number of independent values or quantities that can vary in a statistical calculation without violating any of our constraints. So in other words, degrees of freedom represent the number of values that are free to vary in a data set given certain restrictions. And the way that we go about calculating these is knowing our number of rows and our number of columns. The actual formula is listed here. So what we do is determine our number of rows in a given distribution. and subtract that by 1 and multiply that by the number of columns minus 1. So let's look at the example here on the right-hand side of our two relationships between the variables of gender and marijuana use. For gender, we know that we have two variables here, both our male and female groups. And so we have 2 in our column category. With respect to marijuana use and this ordinal level variable, we have 4 categories at play here. They could either respond never, rarely, occasionally, or often. And so we have 4 rows. And so when we plug both of those in respectively to our degrees of freedom calculation, we get 4 minus 1 equals 3, and multiply that by 2 minus 1, which is 1, to get a total of 3. We'll use this degrees of freedom with respect to our chi-square table or Appendix D here in just a moment. To use Appendix D, we need to take the corresponding degrees of freedom that we just established on the last slide and find the corresponding alpha value cutoff. And so let's say for the sake of argument that we are using a 0.05 alpha level, one of the most common ones we use in statistics. And our degrees of freedom was 3. We need to find the middle point of these two variables. So with a degrees of freedom of 3 and an alpha value of 0.05, our corresponding chi-square critical value is 7.815. So again, that's our critical region or our cutoff value that serves as that barrier of our rejection zone. Another way to visualize this is now that we've established our chi-square critical region of 7.815, is now we can plug this into our barrier of our critical region. And so any value that is greater than 7.815 is going to fall into our rejection zone. And so we will reject the null hypothesis and assume that the two variables are dependent on one another, meaning that they have some sort of association or relationship. If our chi-square obtained value is less than 7.815, we are going to fall into our safety zone or our fail to reject zone. And because of that, we would fail to reject the null hypothesis and assume that the two variables are independent of one another, meaning that they don't have any statistically significant association. Our fourth step is to compute our chi-square test statistic, or our chi-square obtained. Let's first go over this formula one more time before we dive into how we can actually use this to calculate our test statistic. So starting off with our sigma symbol here, this means to sum or to add all of the values together. And so we will have to calculate each observed frequency and expected frequency for each respective cell and add all of those values together. So in this example of a 4x2 bivariate table, we have 8 cells that we will have to do this calculation for. And so how I got that is simply by looking at these cell values here. But you can also do it quickly in your head of the 4x2 table, multiply those two values together to get 8. And so before we can actually add together all these values, we first have to determine our expected frequencies, or what we would expect to see if the two variables of gender and marijuana use are truly independent of one another. And the way we go about calculating that is by taking our row marginal, or our row total, and multiplying that by our column marginal, or our column total, divided by n, or the entirety of our sample. Within a bivariate table, you can always find the n in the bottom right-hand corner because that signifies the total of all of the variables that you'll be dealing with. So let's do an example together of how to calculate the expected frequency for cell number 1 here at the top, which is for males who stated that they often use marijuana on a weekly basis. We first take our row total of those individuals that reported that they often use marijuana, which is 8. We then multiply that by our column total, which is our total number of males within the sample, which is 16, and divide that by our n, or the total number of individuals within the sample, which is 31. And so our expected frequency, or the value we would expect to see in this cell if there was truly no relationship between gender and marijuana use, is 4.129. Keep in mind, we have to determine this expected frequency for each respective cell, so 7 more times, and we'll go through that on the next slide as well. So moving forward with our expected frequencies, I show you here in a couple formats how you can do so. So again, you're taking your row marginal or total, multiplying that by your column marginal, and dividing that by n, or our total of 31. And so the values that you see below our observed frequencies, which is the number you'll see here at the top, is our expected frequencies. So that's me just working through the math for each respective cell. We can then take the calculations of our expected frequencies and plug them into our chi-square obtained formula. And so remember, our sigma sign here means to sum, or to add all of our observations together once we determine their values. And so we'll have to do this for each individual cell. And so we'll take the observed frequency, so the number that is reported in that cell itself, subtract it from the expected frequency, and square that value. That value will serve as our numerator, and then we will divide that also by our expected frequency. Again, we have to repeat this process for each individual cell, and so we'll do this 8 times. Where we get our sigma sign from is that we have to add all of those values together once we determine them. What you'll see here on the left-hand side is me simply working through the math of each of these individual calculations for each cell. Once we take all of those values and add them together, you should get a final chi-square obtained value of 1.680. Once we compute our chi-square obtained value, we can then compare that to our chi-square critical value, which is what we determine in step 3. If chi-square obtained is greater than our chi-square critical, we would reject the null hypothesis and conclude that the two variables are dependent, meaning if our value exceeds our critical cutoff point, we fall into our danger or our rejection zone. If our chi-square obtained value is less than our critical cutoff value, we will fail to reject the null hypothesis and end up in our safety zone, or our fail to reject zone. In essence, that means that our two variables are independent of one another. And so what do we decide here within the context of this problem? Well, our chi-square obtained value was 1.68, which is less than our critical value cutoff that we got from Appendix D of 7.815. And so if it's helpful for you to visually display this as well, I highly encourage you to do that. What you'll see here is my chi-square critical cutoff value of 7.815, and then I map on our chi-square obtained value of 1.680. And so we are clearly in our fail to reject zone here. And so the way we would interpret this within the context of the problem is a little bit different than how we would do it in our traditional hypothesis testing, because we need to use the language of independence versus dependence. And so in this case, we can say we fail to reject our null hypothesis, which is our H0, and conclude that the two variables, gender and marijuana use, are independent of one another. Again, because our null hypothesis is our statement of no difference, we don't have any reason to believe that gender and marijuana use have any association or relationship to one another. So again, chi-square is an easy way for us to compare the relationship between two categorical variables, and that's why they have to be either nominal or ordinal in nature. Let's work through another example together. A judge allows some individuals convicted of DUIs to participate in a treatment program to see if it has any effect on recidivism. In other words, do those individuals recidivate and have another subsequent DUI? Is participation in the program related to recidivism at an alpha of 0.05? So that'll be important for us once we get to Appendix D, because remember, the two elements that we need to establish to determine our critical cutoff is our degrees of freedom and our alpha level. And so you'll see here on the right-hand side, our bivariate table is simply a 2 by 2 in this case. So your status is whether or not you participated in the treatment program or not. So non-participant is going to represent those individuals that did not participate in the treatment program. And then on the right-hand column here, we have those that did participate. In our column of recidivation, which is our dependent variable, we see a nominal level variable of simply yes or no. Did they commit another DUI after either participating in this program or not participating in this program? Our first step is to make assumptions. And remember, there's only two with respect to chi-square. The first is that we have independent random samples. In this case, we know that we do because you either participated in the program or you didn't. The second is that the level of measurement is nominal. Know that it could be ordinal, just like we saw on that Likert scale of marijuana use in the previous example. But in this case, we have two nominal level variables, whether you participated in the treatment program or not, and whether you recidivated or not. Our second step is to establish our null and alternative hypotheses. We will keep the same statistical notation as we did for one sample and two sample hypothesis testing with respect to H0 to designate our null hypothesis and H1 for our alternative hypothesis. Where we'll differentiate here is the actual verbiage that we use to state both our null and alternative hypotheses. There is no numerical information that we can use to designate whether or not there's a certain population proportion or average. And because of that, we simply state the two variables. In this case, it was participation in the treatment program and recidivism. And for our null hypothesis, we'll state that they are independent from each other, meaning our statement of no difference is that we don't have any reason to suspect that these two variables will have an association or a relationship to one another. In our alternative hypothesis, we also state what the two variables of interest are, so again, participation in the program and recidivism, but now we're saying that they are dependent on each other, or that there is some sort of relationship or association between these two variables. Our third step is to select our sampling distribution and establish our critical region. We know anytime we are working with two categorical variables that we will be using a chi-square distribution. So the only other thing we have to do is establish our critical region. Keep in mind that this is a different step for chi-square because we first need to determine our degrees of freedom. And the way we go about that is by taking our row total, -1, and multiply that by our column total, -1. For this particular example, we are working with a 2x2 bivariate table. And so we have 2 rows and 2 columns. And so in this case, our ultimate degrees of freedom is 1. And if you're to look up this value with respect to a 0.05 alpha level on Appendix D, you will see that the associated chi-square critical value is 3.841. Another way to visualize this with the table is, again, go to that corresponding alpha level here on the top with our associated degrees of freedom of 1 to get that critical region. We can then use that number as our barrier point of our fail to reject zone and our rejection zone. So if we get a chi-square obtained value of greater than 3.841, we will reject the null hypothesis. And if we get a value less than 3.841, we will fail to reject the null hypothesis. Our fourth step is to compute our chi-square test statistic. And keep in mind that there's 2 steps we need to complete here before moving on to our actual calculation. The first is to simply identify what our observed frequencies are. And keep in mind that our observed frequencies are simply the numbers that are reported within our bivariate table. So there's no math that you'll need to complete here. However, we also have to establish what our expected frequencies are, or what we would expect to see if these two variables were truly independent of one another. We do that by taking our row marginal, or our row total, and multiplying that by our column marginal, or our column total, and divide by n. And keep in mind, you can always find n by going to the bottom right-hand corner of a bivariate table. And let's work through this on the very next slide. So first things first, we need to establish our expected frequencies for each respective cell. In a 2x2 table here, we know that we'll have 4 individual cells, so we'll have to repeat this process 4 times. What you'll see around this table is me simply working through the calculations for each respective expected frequencies. So keep in mind that you take the row total multiplied by the column total and divide that by our n, which in this case is 406. So using our expected frequencies from the previous slide, we now have enough information to determine our chi-square obtained value, which serves as our test statistic in our chi-squared test. Taking a look at our bivariate table on the right-hand side here, our observed frequencies are here on the top value and our expected frequencies are right below. It's easier for us to compare these two values to one another quickly and just keep track of these two values as we work through the remaining calculations. And so, recall that this is a 2x2 table, and so we're going to have 4 different calculations that we'll need to do and add all of these together to ultimately determine our chi-square value. And so what you see just below this is me working through the math of this. So starting off with the top left-hand cell, which serves as my non-participants, so those that did not participate in the treatment program but did recidivate, I have 120 of those individuals. So my observed frequency was 120, and I subtract that by our expected frequency, which is what we calculated on the previous slide, or what we would expect to see in this cell if our status of participation and recidivism were truly independent from one another. We then square that value and divide it by our expected frequency. So right here you see me working through this as well. Our numerator comes out to a value of 232.837, and we repeat this same process for each respective cell. So the next one would be those that did participate in the treatment program but also did recidivate. And so you'll see our observed frequency was 123, subtracted by our expected frequency of 138.259 squared, divided by our expected frequency of 138.259. And we repeat that same process for each of these 2 cells below as well. Ultimately, when you work through the math, you should receive each of these values here below for each respective cell. But keep in mind, we have to add all of these together. Sigma tells us to sum or to add them to ultimately get a chi-square obtained value of 9.732. So now that we have our chi-square obtained value, we can now compare it to our critical cutoff. Our critical cutoff for an alpha level of 0.05 and a degrees of freedom of 1 was 3.841. That's something we established in step 3 through Appendix D. So mapping this out visually here at the bottom, here is our critical cutoff region, but our X obtained with our chi-square falls into this region. It is beyond or greater than our critical cutoff value of 3.841. Because of this, we reject the null hypothesis. The way that we would interpret this within the context of the problem is that we reject H0, so we reject the null hypothesis, and conclude that participation in the program and recidivism are dependent on each other, meaning that there is some sort of relationship or association between these two variables. Keeping in mind the previous example that we just found, that participation in the program and recidivism are dependent on one another, one thing that a chi-square test can't tell us is in what direction those two variables actually are associated to one another. Is it that the treatment program is having a positive effect on recidivism or a negative effect? Chi-square can't tell us that in the actual result. It can only tell us if there is a relationship, but not necessarily the direction that relationship is in. Because of that, we can start to understand this relationship better, though, if we calculate column percentages. And so we would be able to see in what direction the impact of this treatment program ultimately had. So now we can hypothesize what direction we would expect these two variables to have in relation to one another. So we can ask the question, do participants have lower rates of recidivism? Essentially, what we're asking here is, does the treatment program work? Do individuals who participate in the program not reoffend at the same rates as those that don't participate? In order to determine our column percentages, we can use observed frequencies to calculate each of these. To calculate the column percentages, all we have to do is take our observed frequencies and divide that by our column total and multiply that by a figure of 100 to convert that into a percentage. So starting off with this top left-hand corner cell here, this represents the individuals that did not participate in the treatment program but did recidivate. So we had 120 of those individuals, and we divide that by our column total of 175 and multiply that by our figure of 100 to get a column percentage of 68.571%. We could follow the exact same steps that we just did there using 55 and dividing that by 175, multiplying that result by 100. But to save yourself some time, we know that this column total has to equal 100%. So once you determine one of these cells, all you have to do is take 100%, subtract that by 68.571% to get 31.429%. Like I said, you could follow the exact same steps we did here originally and plug this number in here, and it's going to get you to the same result. So either way is just fine. Just know there's multiple pathways you could get to this answer. But let's compare this top row to our participant cell here on the top. We had 123 individuals who participated in the treatment program also recidivate. And so if I plug in 123 and divide that by my column total of 231 and multiply that figure by 100, I get 53.247%. So these two top cells are essentially what we want to compare. What effect and in what direction did this treatment program have on recidivism? So we're looking at the people that did recidivate. So individuals that did participate in the treatment program only recidivated 53.247% of the time, whereas those that did not participate in the treatment program recidivated 68.571% of the time. So we have about a 15 percentage point gap here. And so what we can conclude is that this treatment program actually lowered the rate of recidivism for participants, because that's what this gap is representing here. And so not only can we determine that there's a relationship between our status of participation or not and recidivism, that's what directly comes from our chi-square test, but now using column percentages, we know that the effect that the treatment program had on recidivism is that it lowered that overall percentage. In summary, we first started today's lecture by discussing bivariate tables, which are also referred to as crosstabs. This is simply a way for us to display statistical information for two different variables. We then moved on to discuss how we could use bivariate tables and crosstabs with relation to a chi-square distribution. So even though this is a new type of distribution for us, we can still use our 5 general steps of hypothesis testing to ultimately calculate our test statistic and make a decision. We first start off by making our assumptions, stating our hypotheses and determining our alpha level, selecting our sampling distribution, which in this case is always going to be a chi-square, while also keeping in mind that for a chi-square, it will always be a one-tailed test. In step 4, we calculate our test statistic, and in step 5, make a decision and interpret the results within the context of the problem. So again, some of this should be reviewed because we're using those same 5 steps that we did in chapter 8 for 1 sample and 2 sample hypothesis testing, but just with a new type of distribution because we are working with categorical variables rather than variables that have a numerical attachment to them. If you have any questions about this material, please feel free to either email me, set up an appointment with me, or stop by my office hours. And as always, I will see you in the next video.